All right, so last time finished up the hip and knee. So this time moving on to the nervous system, sort of a hard transition. But anyway, so there's 3 nervous system chapters. So the first one is chapter 11. It's the fundamentals of the nervous system. So this is going to follow pretty closely to the book. So for those of you that have the book, unlike some of the other stuff like the hip and knee stuff where there's not a lot in the textbook on that, this stuff and the next chapter, which is chapter 12, does. So we got a fundamentals of the nervous system chapter, and then that's going to be followed by chapter 12, which is the brain. And we'll get to the brain probably on Friday, but certainly by Monday at the latest. So as mentioned last time, the plan is to cover fundamentals and then the brain and then review for the exam. So the review will be next Friday, and then the exam will be the following Monday. So close to the next exam already. So as far as the nervous system goes, so when we talk about the nervous system, we're talking about your brain, your spinal cord, and your nerves. So there are 2 primary control systems to the body. The first one, or the more important of the 2, I guess. That's not fair. The one that we associate more closely with being the primary, the predominant controlling system of the body is the nervous system. So again, your brain, your spinal cord, and your nerves. The other controlling system of the body is the endocrine system, which is your hormones. So the nervous system acts much more quickly than the endocrine system does. So you're talking milliseconds in terms of how quickly the nervous system acts. And basically what the nervous system does is conveys a combination of electrical and chemical messages between cells. So in terms of the functions of the nervous system, it basically does 3 things if you want to look at it at its most fundamental level. And the first is that it monitors both our external and our internal environment. So it gathers sensory input or sensory information about both types of environments, external and internal, and then it relays that information, which is the next step, it relays that information back to the brain. So there's an important term on there which is afferent, and that's spelled for you next to sensory input. Afferent information is sensory information. And you'll see that in the context. I'll talk about afferent nerves or afferent neurons. So just know that every time I say afferent, I mean sensory. So there's a couple different broad categories of sensory input. There's conscious sensory information, which is all the stuff that we're aware of. So right now, all of you are probably aware of the lighting level in this room. You can hear me talking. You're aware of the temperature in this room, all of that kind of stuff. That's all conscious sensory information. Something's touching you, something's not, those kinds of things. But we also are aware of unconscious sensory information. So for example, you have sensors in your carotid arteries, in your aorta, and then also in the hypothalamus that monitor things like your blood pressure. They also monitor things like your blood oxygenation. And for example, if you were to fly to Denver or Mexico City at 5,000 and 7,000 feet respectively this afternoon, you would see some rapid adaptations after you landed in either of those cities. So how are you going to adapt to being a mile high or a mile above sea level if you fly to Denver this afternoon? How's your body going to be different or act differently in Denver than it'll act here in Whitewater, which is about 700 feet above sea level? Guesses? Yep. Kinda, yeah. Mostly what you're going to do is your blood won't be fully oxygenated. So here at sea level, your blood is about 98%, or more specifically, your hemoglobin is about 98% saturated. There's some variance in there, but it's about 98% saturated. If you go to Denver, it may drop a little bit, 97, 96%, because of the reduction in barometric pressure. And so to accommodate or to compensate for that lack of oxygenation of the blood, you will then increase your heart rate. So your pulse is going to go up and your breathing rate is going to go up. So all of that is unconscious sensory information. Surely you knew you were in Denver, but you didn't really have to think about like, oh, barometric pressure is going to be lower, blood's not going to be oxygenated, need to increase heart rate. That just happens. That's automatic stuff. So that is unconscious sensory information. So the sensory input then gets relayed to the brain. So gets relayed, for the most part, back to the spinal cord and then up to the brain. And then it's the brain's job to integrate or interpret that information. So the brain is constantly getting a variety of electrical signals. And it's getting those signals from neurons throughout the body. And what it has to do is to make meaning from that information. So for example, everybody in the room at the moment has at least one of their elbows flexed, right? So your arm is bent. And you're aware, without thinking about it, that your arm is bent. Well, how do you know that? And the answer to that question is your brain is constantly getting sensory information from muscle spindles, special receptors inside of the muscle, that's telling it that the muscle is short. And it's getting some information from joint receptors on the anterior aspect of the capsule, but not so much on the posterior aspect of the capsule. And it's able to put all that information together to recognize the position of that particular joint. So again, it's going to take this barrage of electrical signals and chemical signals and convert that into useful information. Oh, my elbow is in flexion, right? Or if you're changing position, it's able to recognize how fast you're changing position based on those same sets of receptors. So based on slightly different information, or really a change in speed and a change of receptor type of that information coming from the muscles, and the same concept in the joints. So the brain makes meaning of the information, and then if necessary, we have a motor response. So for example, if when you leave here, there is some sort of an obstacle in the hallway, maybe like a wet floor sign or something like that when you're walking out of here, you'll see that. That's that afferent sensory information. And then the brain will make meaning of that. Oh, that thing is going to be in my way. And so then you'll get a motor output, which may be that you step to the side, right? And so then that's the motor response to accommodate for that sensory information. So another important term on there, motor responses or motor output, is also known as efferent. So anything efferent is motor. And so when I say motor, think about movement. So a motor response means that there's going to be some kind of movement. That could be movement of a voluntary skeletal muscle. That could be movement of the muscles around the intestines, around the stomach. But a motor response indicates that there's going to be some kind of movement that occurs. So broadly speaking then, the nervous system gets inputs, gets sensory information from the external and internal environments, makes meaning of that information, and then produces a motor output if we need to do that. So the nervous system helps us understand and respond to our environment broadly. All right, so two principal parts of it, or two branches, two big branches to the nervous system. The first is the central nervous system. So the central nervous system includes your brain and spinal cord. So it's all of the nervous tissue that's in those dorsal body cavities that we talked about the first week of class. So central nervous system, brain and spinal cord, and of course peripheral nervous system then, everything else. So all of the nerves that exit the spinal cord, so starting at spinal nerves and then they branch from there, or you have nerves that exit directly from the brain, so those are your cranial nerves. The brain nerves or the cranial nerves are responsible for things like facial movement, facial sensation, eye movement, sense of taste, sense of smell, those kinds of things. Those are all cranial nerves. So they're nerves that exit directly from the brain. When we get to chapter 13, it's going to be less fun this semester because I think by then we're online, but we get to chapter 13, we're going to go over all the cranial nerves and what each of them does, because if you've ever seen someone tested for a concussion or ever performed a concussion test or ever been the recipient of one, whether you remember it or not, they tested cranial nerves. And so I'm going to show you how to do that. So that's part of the peripheral nervous system. So again, peripheral nervous system, every nervous tissue, all the nervous tissue that's not part of the brain or spinal cord. And we're going to branch even further. So the peripheral nervous system can be broken down into an afferent component. And the afferent or sensory component of the peripheral nervous system can be further subdivided, because why not, into both somatic and visceral branches. So the somatic branch of the sensory component of the peripheral nervous system is responsible for essentially conscious sensation. So it is responsible for sensing information from the skeletal muscles and from the joint capsules. So it senses information about proprioception broadly. So proprioception is knowing where you are in space. So an easy way or easier way to think about that, soma means body. So somatic is something that's happening to your body. So again, think about your position sense, your proprioception, your awareness of where you are in space. As opposed to the visceral branch of the afferent branch of the peripheral nervous system. So anything visceral is the organs. So that gives me sensory information about what's happening with my internal organs. So things like whenever your stomach gurgles, or your intestines more accurately, whenever you get that gurgling sensation, or if you have to use the restroom, those kinds of things, that's visceral sensory information. That's what's going on with the organs inside of the abdominal cavity in that case. So that's visceral sensory information. So somatic sensory information, what's happening with the body, muscles, muscle length or lack thereof, joint capsules, and then visceral, what's happening with the abdominal organs or the thoracic organs. The motor branch then, so if we have a sensory branch, obviously we have a motor branch. So the motor branch also has a somatic component. So the somatic component to the motor branch is responsible for voluntary movement. So right now, as I am talking and walking around and moving my arms around and all those other things, I'm getting electrical signals that are originating in the brain, going down the spinal cord, and then out to the relevant muscle cells that are causing that movement. So all of that is occurring through the somatic branch, the voluntary branch of the motor component of the peripheral nervous system. So on the motor side, know that somatic is voluntary movement. So somatic is voluntary on the motor side. Autonomic on the motor side is, autonomic sounds like automatic, so it's all the automatic motor outputs that we get. So, since Halloween is coming up this weekend, if you were to go to a haunted house, I don't know if that's a thing this year, but let's say it is. If you go to a haunted house and you're, walking into a dark room and somebody jumps out at you and scares you, what are the physical responses you're going to have to that fright? How is your body going to respond to that acutely? You might scream, right? But other than that, what else might you do? Okay, you might jump. Yep, so you're going to get some involuntary muscle contraction there. What else are we going to get? Good. So you're going to get an increase in heart rate, and also you're going to get an increase in blood pressure. Your hair is probably going to stand on end, and your pupils are going to dilate. So they're going to open up, right? So you didn't mean to do any of those things. You didn't mean to cause your blood pressure to go up. You didn't mean to cause your heart rate to increase. You didn't mean for your hair to stand on end or your pupils to dilate. All those things happen automatically. So that is part of the autonomic nervous system. And actually what I just described to you was one of the two branches of the autonomic nervous system, which is the sympathetic branch. So the sympathetic branch, what I want you to know about it is it's more commonly known as the fight or flight response. So fight or flight is the set of motor responses that occur when we're startled. But it's actually the same set of motor responses that we get during exercise. So when you're startled, you're going to release epinephrine, norepinephrine, collectively known as adrenaline. And so adrenaline is going to be responsible for increasing your heart rate, increasing your blood pressure, also freeing up glucose, so it's preparing us to run. And all of those things happen when you start exercise as well. So you become sympathetic dominant during exercise. So sympathetic is fight or flight. Parasympathetic then is the opposite, so rest and digest. So the parasympathetic nervous system is dominant at rest, or parasympathetic branch of the motor branch of the peripheral nervous system is dominant at rest. And so it does things like, again, if we're talking about the motor branch, which we are, then you're going to cause some kind of a motor response. And so one of the things that the parasympathetic branch does is it directs blood flow to the organs of our abdomen. So you only have about 5 liters of blood, but if all of your blood vessels were open at once, they could hold about 20 liters of blood. And so we have to engage in what's called blood shunting. We have to direct it to certain tissues at one time and then direct it away from those when they don't need that blood flow. So at rest, your skeletal muscles aren't getting very much blood flow because they don't really need very much oxygen. We kind of open and close blood vessels here and there. So we direct blood flow away from your skeletal muscles at rest, and we direct it to the kidneys, to the liver, to the stomach, and to the intestines. So that's where the rest and digest comes in. So you direct blood flow, or you shunt blood flow to the abdominal organs, so to the digestive and filtering organs. So that's what happens when the parasympathetic branch is active, is we constrict, so that's where the muscle contraction part comes in. We constrict the smooth muscle around blood vessels going to skeletal muscles to direct blood flow away from those skeletal muscles that don't need blood flow right now and to the abdominal organs. And the opposite happens during exercise, or if you're scared, either way. So then with the sympathetic branch, we actually get a systemic vasoconstriction, which means you close blood vessels down throughout the system, but the effect ultimately is to direct blood flow to the working muscles and away from the abdominal organs. Yep. Automatic responses, yeah. So all those unconscious things that you just do. Yep, so all the automatic responses, so whether that is I got to prepare to run or I got to make sure I digest breakfast, those two things. So here's all the same information, just in a graphic, if it helps you. So it kind of lays it out as a tree, if that's a more helpful way for you to view it. So like I said, same stuff, just on there in a different format. All right, so let's talk about glial cells. So in the nervous system, you have two broad categories of cells. So you've got neurons, and neurons are the real stars of the show here. So the neurons are the cells that actually send electrical signals. They communicate with each other to help us learn new information, to help us store memories. They also communicate with muscle cells to cause skeletal muscle contraction. They communicate with smooth muscle to cause smooth muscle contraction. So the neurons then are the cells that actually do the communicating. But in order for them to do their job, they need a bunch of helper cells. And so the helper cells are the glial cells. So neuroglia are helper cells that enable the neurons to do what it is that they need to do. So basically to continue to send electrical signals. So in terms of the glial cells, there are 4 types in the central nervous system. So the first one there, so all of these are central nervous system glial cells. There's 2 other types that we'll talk about in the peripheral nervous system. So this is all central nervous system here. So with the astrocytes, they do a bunch of different things. The astrocytes, one of them is actually pictured there. So the graphic that you see in the lower right, so obviously the yellow thing is a neuron. So again, rock star of the nervous system. And then the red things are your capillaries, so your blood vessels. And then all of this kind of tan thing, that is an astrocyte. So it kind of looks like a star. That's where the name comes from. So the astrocytes do a bunch of different things. The first is that they physically support the neurons. So they act as a sort of scaffold, and you can kind of get that from the picture there, that they sort of act as a scaffolding to help physically support the neurons. But not only that, especially in a developing nervous system, but also to some extent throughout the lifespan, they actually play a role in moving the ends of the neurons around. So neurons communicate with each other, obviously. So the end of one neuron is called the dendrite, and we'll get to that later. Or sorry, the axon terminal. And then the end of another one is called the dendrite. Okay? And so one of the things that the astrocytes will do is they'll move those terminals around to have this neuron maybe communicate with a different neuron. And that plays a role in how we store memories, particularly long-term memories. So the astrocytes, by physically moving the ends of the neurons, can establish new connections between them to help us learn and remember new information. So they play a really important role there. So in terms of support, they physically support them, but they also move the ends of the neurons around to help us learn new information, to help us store new memories. In terms of their blood supply, so one of the things you can see here, the astrocytes have these little things that are called feet. So the feet in this case are wrapping around an axon of a neuron. But over here, you've got the feet of the astrocyte wrapping around a capillary, wrapping around a blood vessel. And so not all of your neurons are active all the time. And so some neurons don't need a ton of blood flow at any given time. At other times when they're more active, they do. And so one of the things that astrocytes do is they can actually clamp down their feet a little bit to close off blood flow if that particular neuron doesn't need very much. Or if that neuron is really active, they can relax their feet, as it were, and increase the diameter of that blood vessel and increase blood flow to that particular neuron. So they're responsible for the blood supply. And then the last thing on there is the chemical environment. So the way that neurons conduct electrical signals is by movement of ions. And ions are electrically charged particles. So in particular, what happens is you get this flux, this movement of sodium and potassium. When a neuron is at rest, and we'll talk about this a lot, when a neuron's at rest, there is primarily sodium outside of the cell, primarily potassium inside of the cell. When a neuron sends an electrical signal, sodium moves inside, potassium moves outside. And in order for neurons to continue to conduct electrical signals, to continue to communicate, we have to reset that original resting membrane potential. So one of the ways to do that is to remove some of that potassium from that extracellular space, from outside of the neuron. And so that's one of the jobs of the astrocytes, is to mop up or clean up some of that potassium to restore that original membrane potential to allow that neuron to keep conducting electrical signals. So in terms of being a helper cell, the astrocytes then can clean up potassium to help the neuron be able to continue to reestablish those gradients so that it can continue to send electrical signals. Another thing that they can do is when two cells are communicating with each other inside of the brain, one of the neurotransmitters, which is a chemical signaling molecule that moves from one cell to another, is called glutamate. One of the really important ones is called glutamate. And so one of the things that the astrocytes can do is they can clean up that glutamate. Because if too much glutamate stays in that space between those cells for too long, it'll keep attaching to chemically gated channels, and it'll keep calcium channels open. Why that matters, too much glutamate sticking around for too long keeps calcium channels open too long. Then you're going to get this big influx of calcium into a neuron, and calcium is going to interfere with the cell skeleton of that neuron. And why that matters is when that calcium interferes with the cell skeleton of the neuron, you're going to get a clumping of some of the proteins inside of that neuron. And those clumpings of proteins then can lead to the death of the cell. And so if our astrocytes are functioning correctly, they should clean up that glutamate to keep those channels from being open too long, to prevent that influx of calcium in the cell, and hopefully to prevent cell death. So the astrocytes do a number of different things, but one of the more important ones is, in addition to blood supply, is to clean up that chemical environment around the cell, both with respect to neurotransmitters, particularly glutamate, but also potassium, so the cell can keep sending signals. So those are the astrocytes. Yep. Yeah, so for the most part, it is genetically determined. I haven't seen anything about like how you would make more of them, or how you would, other than like Alzheimer's, I'm not aware of anything that specifically damages them. I would imagine some traumatic impacts can cause damage to the astrocytes, but I haven't seen specific research about that, so I don't know. So let's go with genetics at the moment. Good question. All right, so we'll talk more about astrocytes in a second on the next slide, because again, they are pretty important. But a little bit less interesting, but certainly no less important, are the microglial cells. So the microglial cells are immune cells that live inside of the brain. So one of the things I didn't talk about with the astrocytes that I probably should, so you've probably at least heard the term blood-brain barrier. And what that means is that the brain has extra protection from things crossing from the blood and moving into the brain. So for example, things like viruses and bacteria, it's especially important for our continued survival that we do everything we can to prevent those things from getting into the brain. And so big molecules can't make it into the brain. And that includes things like macrophages. So macrophages are a type of white blood cell. If you damage a tendon or damage a muscle, macrophages are going to go in and clean up that damaged collagen. And then we can lay down new collagen, we can repair stuff. In the case of the brain, though, because macrophages are so big, they can't cross the blood-brain barrier. And one of the layers of the blood-brain barrier is actually these little feet of the astrocytes, so that the macrophages essentially can't get in this gap. And so because we can't get the cleanup crew, if you will, from the blood into the brain has its own special cleanup crew, which is the microglial cells. So when a neuron dies, those proteins, those phospholipids, et cetera, have to be cleaned up, and it's the job of the microglial cells to do it. So know that the microglial cells are the immune cells. They're the cleanup crew of the central nervous system. The ependymal cells beat your cerebrospinal fluid. So they move your cerebrospinal fluid around. So your cerebrospinal fluid is the fluid that the brain and the spinal cord float in. It's kind of a straw-colored fluid. And so that plays a really important role in protecting the brain. So that's one of the things where if you hit your head, you have this sort of fluid layer of protection that'll keep the brain, unless it's a really intense trauma, that cerebrospinal fluid helps keep the brain from impacting the skull. So the cerebrospinal fluid then serves a protective function. It also helps the brain get rid of waste products. And so the ependymal cells then move that cerebrospinal fluid around to help get rid of those waste products. So that's kind of their job. So in some ways they're a cleanup crew too, but they're not immune cells. So they beat the cerebrospinal fluid, they move the cerebrospinal fluid to help get rid of waste products. And then the last thing on there, it's a fun one to pronounce, oligodendrocytes. So oligodendrocytes are cells that perform something called myelination. And myelination, a way to think about it, is insulation of neurons, and specifically of the axon, AXON, of a neuron. So what myelination is, and so you spell myelination M-Y-E-L-I-N-A-T-I-O-N, myelination. So what myelination is, again, insulation. So it's a fat wrapping around neurons, and it helps them send their electrical signals faster. So almost all of our neurons are myelinated. So they're covered in myelin, and that helps us conduct electrical signals really quickly. Not all of them, but the vast majority of our neurons are myelinated. The ones that are unmyelinated send their electrical signals much slower. As we'll talk about when we get to the peripheral nervous system, if you have sort of just like an aching pain, so let's say you have trochanteric bursitis, one of the things we've talked about, one of the symptoms that people often complain of is like just when I sit there in class, like my hip just aches. That like low intensity aching pain travels over unmyelinated nerves, because we don't need to get back to the brain really fast. We just need your brain knowing that something hurts. And so that slow aching pain travels over unmyelinated nerves. As opposed to if you touch a hot stove burner, that travels over myelinated nerves, because I need to know that information quickly that hurts, right? So there's different the myelination affects how fast the brain is aware of what's happening. So if I'm burning myself, I need to know that right now. If my hip is just kind of aching because I've got arthritis, I need to be aware of it, but I don't need to be aware of it right now. And so myelination, fast signals, unmyelinated, slow signals. So the oligodendrocytes then are cells that myelinate the nerves in the central nervous system. Yep. Yeah, so part of it is that the brain has to process that information. The information is getting back to the brain really quickly, but it has to be able to process it. And then part of that processing too is kind of some awareness of the other dangers that are going on. So if you're cut, maybe you're cut because you got bit by a snake, or there's something else dangerous going on. So you're also processing a bunch of sensory information, other sensory information at the same time that's kind of fight or flight, like do I need to go kind of stuff. And so that's why the brain doesn't register, or you're not consciously aware of that pain for a couple seconds, is because you're kind of processing that other, like, are there any other dangers? Oh no, crap, I cut myself. Now it hurts, kind of a thing. Yeah. So yeah, that's how that works. And this we'll talk when we get to the, I think it's in the peripheral nervous system. But one of the things that the brain can do is basically choose not to acknowledge that pain. It's called descending pain control. Actually, I may talk about that in chapter 12. But you've probably experienced that to some extent yourself. Like you see athletes who maybe they rolled their ankle in the state championship game of their senior season, and they just fight through it. And then after the game, they're like, oh my God, it's the worst pain I've ever had in my life. But during the game, it didn't bother them. That's part of that descending pain control, where the brain is getting those signals, but it's just choosing not to acknowledge them. And so then you are not consciously aware of it. And so we'll talk about how that happens. So it's a similar kind of a thing, that you're just like, I'm going to tune that out for a second. Let's see what else is going on. Okay, I'm good. Now that hurts. Yeah. We also see that too, having a 10-year-old, where if kids are around their friends, stuff doesn't hurt. But like as soon as the friends are gone, like, it's the worst ever. And so that's social factors play a role in pain as well. Yeah. So then we got the neurons. Like I said, we'll talk about them in a second. All right. So a quick bit about Alzheimer's disease, because I talk so much about the astrocytes. So one of the things where astrocytes are really important, or where they come into play, is with Alzheimer's disease. And so early stage Alzheimer's disease, one of the classic characteristics of it is that you get an atrophy, a shrinkage of the astrocytes. So the astrocytes, some of them shrink, some of them die, so there's just fewer of them. And so that actually plays a role in the development of Alzheimer's disease. And just as a historical aside, so the first patient diagnosed with Alzheimer's disease was a German woman in 1906 who went to a psychiatrist whose name was Alois Alzheimer. And he worked closely with another psychiatrist, Emil Kraepelin. And so the woman, Auguste's husband, brought her in because she had just become irrationally jealous of him. She had decided that he was cheating on her even though his behaviors hadn't changed. She had no good reason to believe that, but she was convinced that he was cheating on her. And so the husband brought her to the psychiatrist, brought her to Alzheimer's and said, look, here's what's going on. I don't know what's happening. Can you see if you can figure it out? And so during the course of his work with her, Alzheimer noticed that not only was she having these irrational beliefs, but she also was starting to have some memory issues, particularly with respect to short-term memory. So she couldn't remember what she had done a few hours ago. She remembered things from her childhood, so your longer-term memory, she was aware of those things. But the things that she had done today, or maybe even yesterday, she didn't remember those. And of course, that got worse and worse to where she couldn't remember people she met. She couldn't remember, and now I'm kind of describing a more broad, I don't know if this actually happened with August, but more broadly, Alzheimer's disease, what you're going to see as it progresses is, maybe they forget the names of their kids. Maybe they forget the names of their caregivers, those kinds of things as it gets progressively worse. And in addition to that, you get a progressive loss of cognitive ability, so less processing, right? And so after her death, Alzheimer did an autopsy on her brain. And so in looking at her brain, he found that her brain had decreased brain mass. It had shrunk. And so this is obviously a generic thing because the original case was from 1906. But you can see a healthy brain there on the left and a brain with Alzheimer's there on the right. And so you can see how the brain on the whole has shrunk. So decreased brain mass. But in particular, when we look at the brain of an Alzheimer's patient, there's a couple of really characteristic things. And those two characteristic things are amyloid plaques that are outside of the neurons. So when we say extracellular, it means outside of the cell, right? So you got plaques that build up outside of the cell. And so what happens there is that you have proteins in the membranes of the neurons that we have to turn over pretty regularly, just as part of normal cell maintenance. And so those proteins kind of gather in that extracellular space, and they're kind of a sticky protein. And one of the jobs of the astrocytes is to clean that up, because again, they help maintain that extracellular environment around the neurons. Well, if your astrocytes shrink and die, they're not going to be able to do it. And so those plaques build up, and they actually build up but kind of between the neurons. And so then that keeps the neurons from interacting with each other. It keeps them from sending good signals to each other. And so one of the things is that short-term memory is essentially that you get a strengthening of the relationship between two neurons. It becomes easier for them to send signals between each other. And so if you have a plaque there, if you have a physical barrier that's preventing those two neurons from communicating, well, I can't remember then what I had for breakfast, or I can't remember whether I turned the car off or anything like that. The other thing that distinguishes Alzheimer's disease is neurofibrillary tangles. What's that? So neurofibrillary tangles are damage to the cytoskeleton of the cell. So I mentioned this earlier, but effectively what happens is neurons have 4 parts to them. So I'm giving away a later slide, but that's all right. It makes this make more sense. So broadly speaking, neurons have 4 parts. So neurons have a body. So the body is this main part here. And the body contains the nucleus, and it contains the ribosomes, which manufacture proteins. And in addition to the body, we also have dendrites. So dendrites receive signals from other neurons. Then we have an axon. And the axon is kind of like a long electrical cord that then projects out and communicates with other neurons. So we have the axon here, and then we have the axon terminals that are going to communicate with an adjacent neuron. So where those plaques build up would be in this space between these two neurons. So again, you're going to prevent the electrical and chemical signaling between those cells. Chemical in this case. And then why all the parts of the neuron matter is the neurofibrillary tangles happen along the axon. So essentially what you do is you manufacture proteins in the body of the neuron, so things that we're going to need at the axon terminals, so things like the neurotransmitters like glutamate that we're going to send. Manufacture that in the body, and we have to transport that down from the body down to the axon terminals. And we do that using the cytoskeleton. So one of the ways to think about the cytoskeleton of a neuron is kind of like train tracks, at least insofar as they're in the axon. And so we transport proteins from the body down the axon to the axon terminals. And where those neurofibrillary tangles occur is primarily in the axon of that neuron. And so if you've got this buildup of tangles of proteins, that neuron then can't send electrical signals down as effectively, right? Because you've got some tangled proteins in there. And we also can't transport things down to the terminals of the axon. So that neuron can't function. So those neurofibrillary tangles then kill those cells. So if we get neuron death, then we get the death of memories. We get the death of neurons involved in things like helping me process information. We get the death of neurons involved in things like decision making. And so those combinations of things then, so one of the things you get if neurons die is, so most of the cell bodies, and we'll talk about this in chapter 12, most of the cell bodies are out here in the most superficial part of the brain called the cortex, and then this inner part is all the axons. Those are tracts. And so if you get this widespread death of neurons, well then the cortex thins out, the size of the tracts thins out, and so that's what accounts for the shrinking of the brain. So where all that's relevant to what we just talked about is those two things, the extracellular plaques and then the intracellular tangles. A lot of that is caused by the shrinkage of the astrocytes. Because they can't maintain that external environment, that then allows for these things to happen. So there's some sort of genetic programming that allows for the death of, or the shrinkage of, those astrocytes that then precedes Alzheimer's disease. And if you can figure out what causes that, then you'll be doing the world a great service. And certainly there is some genetic predisposition. So there's a particular lipoprotein. It's a combination of a fat and a protein. Allele, so there's 4 different variants on the protein. If you have the E4 variant, you're much more likely to have Alzheimer's disease and potentially much more likely to get chronic traumatic encephalopathy, which is the disease that afflicts football players and boxers, people that get repetitive brain injury. If you have, I think, the E1 allele, you're much less likely to get either of those things. So certainly there's a genetic component to these things. So yeah. Excitotoxicity, I didn't really talk about what that is. So excitotoxicity is where, I did talk about it, but I didn't tell you what it was. So that's where there's glutamate hanging out in that space between the neurons that's allowing for calcium movement influx into a cell. So that's excitotoxicity, because that'll be important here in a couple of slides again. And that calcium influx is what actually interferes with the cytoskeleton that allows for those neurofibrillary tangles. So those things are related. So too much glutamate outside of the cell causes the opening of calcium channels. Calcium moves into the neuron. Calcium interferes with the cell skeleton. You get tangles inside of the cell, kills the cell. And you see a similar process with CTE, the brain injury again with boxers and football players. There's a similar relationship where you get some level of excitotoxicity and damage to the cell skeleton. All right, so as mentioned, the glial cells I just showed you were glial cells in the central nervous system. So now we're in the glial cells of the peripheral nervous system. Not nearly as interesting. So there's 2 there, 2 major types. So you got satellite cells that are similar to the astrocytes in the peripheral nervous system. So they're called satellites because they're around the cell body in the peripheral nervous system. So what you've got here is an afferent or sensory nerve or neuron. And so here's its little cell body here off to the side. And then it's got satellite cells around it. So they're called satellite cells because they're around the cell body, kind of like satellites around the Earth. Similar idea. And the moon is a satellite, right? So they're around the body. And then Schwann cells are the cells that myelinate the peripheral nervous system. So oligodendrocytes myelinate the central nervous system, so the brain and spinal cord. Schwann cells myelinate the peripheral nervous system, so everything outside of the brain and spinal cord. All right, so neurons, some of this stuff I've already told you, but that's okay. So again, neurons are effectively the rock stars of the nervous system. They're the ones that send electrical signals, the ones that actually do the communication, that cause the muscle contraction, that store memories, etc. So we're going to skip over what nuclei and ganglia are for now. We'll come back to that. One of the things about the nervous system, and you can actually get a good idea of it from this picture of the brain, is that nervous tissue is really, really dense. So your brain has somewhere in the neighborhood of 86 billion neurons in it, in addition to those other 4 cell types that we talked about. So there's a lot of cells in a relatively little space. And that made studying the brain really, really difficult until the late 1800s, when a scientist named Camillo Golgi injected silver nitrate into the brain of some kind of an animal. I don't remember what kind it was, doesn't matter. But the neurons take up that nitrate, and then the rest of the extracellular space, the astrocytes, et cetera, don't. And so that helped us to envision what a neuron looks like. So what you're seeing there in that picture, that is that silver nitrate injection. That is that Golgi contrast. And so all the black stuff is a neuron, and everything else that's not black is not neuron. So then a Spanish scientist in the late 1800s, whose name I'll butcher, so I'll skip it for now. His last name is like Ramon y Cajal. I think it's Santiago Ramon y Cajal. Anyway, late 1800s. So he used that silver nitrate contrast to look at the brains of developing animals, because their neurons are much simpler, to come up with neuron theory. And so what that is what I just described to you. Basically, that a neuron has 4 parts to it. And so those 4 parts include the dendrites, the body, the axon, and the terminals. And so that's kind of been our operating framework since the late 1800s. So in terms of characteristics of neurons, other than what they do, so they're unique from other cells in several ways. The first is that they essentially last as long as you do. So they have extreme longevity. So neurons last, for the most part, your entire lifetime. So and bone cells, osteocytes, once they mature, also last for a really long time. So those also have pretty good longevity, but not quite as long as neurons do. So neurons, for the most part, last for your lifetime. They are amitotic. So if a cell undergoes mitosis, it means that it splits and makes an exact copy of itself. So we talked about that with the growth plates and chondroblasts. Remember, for the growth plates to grow, one of the first parts of that is that the chondroblasts in that growth plate are going to make a bunch of copies of themselves, and then those will grow. Well, that's mitosis, is when they're splitting and making a new chondrocyte. In the case of neurons, they are amitotic, meaning that they can't make copies of themselves. They can't split and make a new one. So a couple important things here. The neuron lasts your whole life, and it can't split and make a new one, so we can't just replace them. So if a neuron dies, it's gone. And as you can imagine, that's a problem. So then that's one of the things that leads to the symptoms that we see in Alzheimer's disease. If a neuron gets neurofibrillary tangles and dies, we can't just make a new one. It's gone. So that's problematic. And then the last thing on there is high metabolic rate. So for the most part, they are pretty active. They demand a pretty constant supply of oxygen. Now, it's higher at other times than others. There's times when, when you're thinking about solving a math problem, the front part of your brain is going to need a lot more blood flow than it does when you're just like sitting around watching TV. But at all times, it needs a pretty good amount of blood flow, because one of the things that we have to do is to maintain those gradients of sodium and potassium. And so that takes a lot of energy. So the neurons then need a pretty high or pretty consistent rate of glucose supply, but also oxygen. So high metabolic rate. They're running through lots of oxygen, lots of glucose all the time. And so again, in terms of the parts of a neuron, so I mentioned neuron theory. So this is kind of a generic motor neuron, was what I'm showing you here. So again, you got the cell body here, the dendrites. So another important thing to understand about neurons is that the electrical signals only go one way. So the dendrite receives a signal from another neuron, and then that initiates an electrical signal that starts at the dendrites, moves through the body of the cell, then down the axon, if I get my mouse to come up, down the axon, and then out to the terminals. So signals only go one way, which explains why we have 2 sets of neurons. You have sensory neurons that relay information from the body back to the brain, because their signal goes that way. And then you have motor neurons, or efferent neurons, that go the opposite. So they start in the brain and go down. So the signals only go one way. They go from the dendrites down to the axon terminals. So related to the last slide, amitotic, again, once it's gone, it's gone. I can't get the sound on this, but it's a clip from one of the old Halloween Simpsons where Lisa comes in and says that Bart's a vampire. And the key line is that Homer's response is, "Oh, Lisa and your stories. Bart's a vampire." And then he says, "Well, let's go back to that building thingy where our beds and TV is, because beer kills brain cells," right? And so the joke there is that, that I totally butchered that line, but the joke there is that he thinks it's ridiculous that beer kills brain cells, and then he can't remember what the name of his house is, right? Or that a house is the name for where he lives. So the question is, does alcohol kill brain cells? And the answer is yes. So alcohol is a neurotoxin. So neurotoxin, something that kills brain cells. And so one of the ways that it probably does that is actually related to the way that alcohol works. So one of the things that alcohol does is that it inhibits glutamate receptors. So remember, glutamate, when a cell receives, it's going to allow calcium into the cell, plays a role in the signaling process. And so if we inhibit glutamate, we inhibit that neuron. So it can't get signals from other neurons. And so if you inhibit neurons in your prefrontal cortex, the front part of your brain, that's where you make conscious decisions. That's where your conscience is. That's where you decide this is a good decision or not. And so if we keep neurons from firing in that part of our brain, well, that then makes things that would otherwise be bad decisions, now those are good decisions. But it also is what makes alcohol effective as a social lubricant, right? You may talk to somebody that you wouldn't otherwise talk to after consuming alcohol because you've inhibited those neurons that would be responsible for sort of your self-consciousness, right? So if you inhibit those, now you'll engage in behavior that you wouldn't otherwise. So that's one of the things, or one of the reasons that people like to drink alcohol, right? And it sort of quiets that thinking part of your brain. But once we remove the alcohol, then those same glutamate receptors become hypersensitive to glutamate. So in the rebound, as it were, then they become hypersensitive to glutamate. So now they open up those calcium channels for a long time. Again, you get excitotoxicity, the thing I mentioned related to Alzheimer's disease. You get excitotoxicity, you get neurofibrillary tangles or things similar to them, and you get cell death. So in long-term alcohol abuse, we also see brain shrinkage. So you see normal brain there on the left, a 57-year-old man with a history of heavy alcohol use there on the right, and you can see the pretty pronounced brain shrinkage. So if you get neuron death, just like we saw with Alzheimer's disease, then you get shrinkage of the brain, right? So, and actually alcohol-related dementia is the second most common dementia in the US, just behind Alzheimer's disease. So in addition to some of the neurotoxicity stuff, one of the other things that tends to happen with people who abuse alcohol long-term is they tend to develop deficiencies. So we all probably are at least aware that if you want alcohol to be more effective, what you can do is consume alcohol on an empty stomach, right? Because the faster you can get alcohol into your small intestine and you can increase your peak blood alcohol concentrations, the more pronounced the effects are. So that's one of the reasons that if you consume alcohol in pure liquor form, so if you're drinking vodka as opposed to beer, you tend to get a faster effect. There's a higher concentration gradient pushing the alcohol into the bloodstream, get a faster, more pronounced effect. And so one of the things that people who are alcoholics tend to do is to not eat very much because it makes the alcohol more effective, right? And so then you can develop a variety of deficiencies, and one of the more common ones is a thiamine deficiency, which is B1. And so thiamine is found in things like pork, spinach, corn flour, beans, and brown rice. And so if you develop a thiamine deficiency, that also then plays a role in getting specific lesions in the brain that will produce some of that dementia as well. So yes, Lisa was right. It is not a story. Beer does kill brain cells. Now that said, I'm not telling you never to drink, because one, that would be hypocritical of me, and two, I recognize we're in Wisconsin. But just something to be aware of, that there is some truth to that. All right. So that's enough for today, because I'm actually over time. So we'll pick up with this on Friday. We'll finish out chapter 11 then, and then time permitting, move on to chapter 12. And then